Good day everyone. So this is our subject, design of steel structures, and I'm Engineer Ronjan R. Garming. So the content of this presentation is about the introduction, the structural design, the structural systems, and then idealized structures, and design specification references, as well as structural steel. So first, the main purpose of this subject is to design the structural components of your building. Of course, it will include several processes into it, and the prerequisite is of course the structural analysis. Why perform design? Of course, in building design, there are two professionals or several professionals that needs to address the safety and serviceability of the building. So serviceability is the appearance and performance in deflection. So of course, the building is subjected to permanent and transient loading. And then another thing is to make the structure economical. Normally, steel structures costs minimal on materials but more on labor and other costs. It is more on equipment requirement as well as the labor cost. So analysis should come into several alternatives, then come up with the appropriate cross sections of the elements and its components. So similarly on the process of reinforced concrete design. All in all, structural designs made to make a sound and economical design to ensure the structural integrity of the building. So this is our concern. So structural systems. The combination of structural elements to act as one to resist external forces referred as structural systems. So we have learned that there are several types of structural elements. So these are trusses, frames, cables and arch, and then surface structures. So to give you an overview, we have trusses. Of course, we have learned from our previous subjects that these are just as merged structural elements or structural members formed in triangular configuration. So these are built to support large spans, carry roof loadings, and provide horizontal stability such as bridges and towers. So we also have cables and arches. So these are series of cables and members usually advantageous to a long span bridges. So as an example, you can see in the photo, San Juanico Bridge in Leyte supports greater spans. Okay, so it has the feature of the reverse curvature. So that is actually adopted in early times, the principle of reverse curvature. Okay, and then we have also the frames. These are combinations of columns and beams as well as trusses under three-dimensional configurations. So I think you are very familiar with the framing system. So frames are usually analyzed as indeterminate structure. So frames could be in the form of steel structures or reinforced concrete structure or the combination of both. And then we have the surface structures. These are actually folded plates of small thickness features light material which permits economical framing systems. Folded plates or shells as well innovates architectural wonders. So the constraint in the surface structure is that the availability of material, because these are special structures. So in our structure, there is a support, okay, and that is called the support reactions. So these are placed to a structure in order to prevent movements of the members due to external forces. So it tends to restrain and maintain the equilibrium in the whole structure. So whether your forces is horizontal and vertical translation, or it could be a rotational effects. The types of support reactions are shown here. This is just a recall on your mechanics. So first we have the light cable, okay, and that light cable by the free body diagram is actually acting in tension. So the number of unknowns is 1, and the reaction is a force that acts in the direction of the cable or the link. The second reaction support is the roller. Of course, there is a restraining axis, okay, and a free axis for the reaction. So meaning one of the axes will be freely moving, okay. So the reaction is a force that acts perpendicular to the surface at the point of contact. So your reaction could also be a smooth contacting surface. So of course, the principle here is the reaction force is always perpendicular to that surface. We also have here smooth pin connected collar, okay, and the smooth pin or hinge. So smooth pin or hinge is restrained on two axes, normally that is the vertical and the horizontal axis. We also have here the slider. So the slider will restrain the rotation as well as the horizontal force. And the last support is the fixed support, wherein all of the forces will be restrained in the support, the vertical, the horizontal, and the rotation. So these are typical examples of the hinge supports. So it might be present in the steel framing system, you can see, and on your door. So those are the door hinges wherein it is restrained between the connection of two elements and has the ability to swing. So that concept is also adopted in some of the bridges. If the bridges is to be folded, okay, like the under the bridge, you can see there, it needs to be folded for the provisions of boat passing under it. So this is the actual example of the roller or rocker supports. So in this case, the roller is free to move sideways. Next, we have here the fixed supports. Of course, that is restrained. So it is normally found in structural systems like reinforced concrete and structural steel framing system. So in the structural steel framing system, if the Support is welded. Of course, it is restrained on 3 axes. So in our analysis and evaluation, we need to idealize our structure. So the idealized structure is actually the structural model of our analysis. So it is the process of replacing actual structures that serves as structural member or model essential to structural analysis. I think you have already known this. So as an example, we have here a cantilever steel section connected to the column. Of course, basically, that will be represented by a framing system. And a floor system here is composed of series of beams, girders, and columns with the joists and slab. So we'll just have to represent that into lines. Okay. So those are typical idealized structures compared to the actual structures. So in here, we have here a model wherein the concrete block walls will serve as the vertical support. In it, we have the wooden beam and the girder underneath. So the representation is that, of course, normally the actual structures are represented by a contact force, okay, and that will be converted in pressure, and that pressure will be eventually resolved into a resulting force. Okay, so the thing here is just, let us just convert the pressure force into a single resultant that will be placed in our idealized structure. So similarly in trusses, so series of trusses are normally welded or bolted on joints connecting series of members to form a triangular configuration. But in idealized structure, it is implied that these connections will be just represented by the connected framing system or truss members. So moving on to the loadings. So there are several types of loadings. We have the dead loads, live loads, highway bridge loads, railroad bridge loads, impact loads, the wind loads, snow loads. Of course, we are not so much concerned on that. Then the earthquake loads, the hydrostatic and soil pressure. So dead loads are actually the permanent weight that are attached to your building system. Hence, for a building, the dead loads include the weight of the columns, beams and girders, the floor slab, roofing, walls, windows, plumbing, electrical fixtures, and other miscellaneous attachment. So as we can see, of course, we cannot neglect the self-weight of your structural elements. In our structural code, you can find the various materials with its unit weight for the computation. Of course, basically, we'll just have to use the formula gamma is equal to the weight all over volume. That could be in terms of kilonewton per cubic meter. And of course, solving for the weight, is equal to gamma times the volume. So we can also see in the specifications various weight of walls, frame partition and walls. So these are elements with the framing system, or if we have a plastered faces of these elements, there are derived values for the weight or the unit weight. Next is we have the live loads. So live loads can vary both in their magnitude and location. They may be caused by the weights of the object temporarily placed on a structure, moving vehicles, or natural forces. Actually, live loads are transient in nature. Of course, they come and go. It's not permanent on the building system. So it depends actually on the occupancy of your live load. Live loads are those loads produced by the use and occupancy of the building or other structure that do not include dead load, construction load, or environmental loads, the load to which a structure is subjected in addition to its own weight. So again, in our code and the international codes present are the various values of live load according to the occupancy or use. Say we have assembly areas like theaters, the office buildings, storage, warehouse, residential, and even schools. So this is called from the ACI 318-19. Actually, these are factors for live load reduction. So live loads are actually reduced in a sense that the effect or the loads coming from the live loads is not more likely on simultaneous, no? So I mean, hindi lahat ng live load ay sabay-sabay in a certain time. So that is the reason why we need to reduce live loads. Of course, the purpose of it is also to economize your design. Okay. So the live load reduction is normally governed by the influence area. That is the product of the live load element factor KLL as well as the tributary area. Okay. So we need to reduce live load for members supporting one floor up to the limit not less than 40% of the original design live load. And no reduction is allowed for loads exceeding 100 pound per feet squared, or that is 4.79 kilonewton per square meter, or for structures used for public assembly garages or roofs. So the term here is the public. Of course, mas maganda yata hindi natin i-reduce yung live loads for the public assembly garages or roofs for safety, because public use is, it is always there, no? So we also have highway bridge loads, wherein we have the H varies from 20 tons to 30 tons, depends on each series of the truck year specification where it is reported. Well, anyway, should be a separate topic, but for your reference, the specification or the design load criteria will be found in AASHTO LRFD bridge. Similarly, on railroad bridge loads, so specifications can be found by published book by the American Railroad Engineers Association. So E-loads as originally devised by Theodore Cooper in 1894. Okay. So aside from that, of course, we have the impact loads, because the loads are sometimes tends to bounce, okay, or moving sideway, so that will cause impact to your structure. So these factors generally obtained from formulas developed from experimental evidence. So this will be the formula for the impact load. So of course, wind loads. In our country, we are vulnerable to storms, okay, that is associated by heavy rains and wind loads. Of course, that would create the wind kinetic energy translated to potential energy or pressure. And when it is absorbed by your structure, it will become its wind load. Okay. So of course, heavy winds or gustiness would cause a lot of devastation on our structure, as witnessed previously. So in international context, we have the snow loads also. Of course, the snow loads will be directly carried by your roof. Okay. So the basis on the design will be general shape, roof geometry, the wind exposure, location, its importance, whether or not it is heated. Of course, just like the wind load, the earthquake load, snow loads has also the zone maps, because there are different intensities. So just to flash it for your reference, for our consumption, it will be found on ASCE 7-10 empirical formula for a flat roof considering the snow loads. Okay. So here, since we belong to the Pacific Ring of Fire, our country is also vulnerable to ground shaking. So seismic loading is one of the basic concepts of earthquake engineering, which means application of an earthquake generated agitation to a structure. It happens at contact surfaces of a structure, either with the ground or with the adjacent structure, or with gravity waves from tsunami. Seismic loading depends primarily on earthquake parameters at the site, the geotechnical parameters of the site, and then of course present here, note that we have the structures parameters, then the characteristics of the anticipated gravity waves from tsunami if we are nearby seashores. Okay. So the earthquake loads provisions in the design will be found on section 208, earthquake loads, under National Structural Code of the Philippines. In here, we have various procedures in dealing with the earthquake loads. We have the simplified static force procedure. We have the horizontal distribution, vertical distribution, and then the static force procedure. We need to compute the design base shear. So actually, static force procedure is the commonly teach in the academy. We have the structure period T, elastic fundamental period, vibration under consideration. So the computation could be method A or method B. And then here, the dynamic analysis procedures. And nowadays, in engineering, performance-based design is also advocated. Of course, we have the formula for the base shear in earthquake engineering. So basically, we have V as the base shear. So it is the maximum lateral force that will occur due to seismic ground motion at the base of the structure. So in your theory of structures, of course, all of the forces are given. But in actual practice, you should determine that parameter by the computation of the lateral force, and that is the base shear. So we need some coefficients, and those coefficients could be found also in our code. We have the seismic coefficient, depending on the soil type and the seismic zone. Of course, we'll refer to the zone map. And then the seismic importance factor. So the importance factor will be different for various occupancy like residential, hospital, garages, and the like. We also have the response modification factor. So it depends on your framing system. T is the seismic time period of the structure, and W is the total dead load of the structure. And I think this will be performed in a separate subject called earthquake engineering. So for our consumption, just be aware that NSCP provides also those mentioned seismic coefficient. We have the soil type, seismic zone factor, near source factor, seismic coefficient CAN, seismic coefficient CV. And the importance factor could be also found in table 28-1 together with the response modification factor. Of course, those are the tables. So finally, we have another type of loading, the hydrostatic and soil pressure. Okay, I think you've already encountered this. So when structures are used to retain water, soil, granular materials, the pressure developed by these loadings becomes an important criterion for their design. Examples of such types of structure include tanks, dams, ships, bulkheads, and retaining walls. The laws of hydrostatics and soil mechanics are applied to define the intensity of the loadings on the structure. So moving on to the design specifications. Of course, I'll just present here where to find those design specifications. So these are based on the latest good engineering practice to enable engineers to adhere with the latest building codes. Of course, in adherence to that is the safety of your structure. Specifications are published by the following organizations. First, we have the AISC, or what we call the American Institute of Steel Construction. So these specifications provides for the design of structural steel buildings, their connections. It is the one of the primary concern, and we discuss it in detail. AISC 2010A, American Association of State Highway and Transportation Officials. These specifications covers the design of highway bridges and its related structure. It provides structural materials that are normally used in bridges, including steel, RC, and timber. So we also have the AREMA, or the American Railway Engineering and Maintenance of Way Association. The AREMA Manual for Railway Engineering covers the design of railway, bridges, and related structure. This organization was formerly known as American Railway Engineering Association. Class, we need to know all of this organization because later on you will be searching for references in your design guide. We also have the American Iron and Steel Institute, or AISI. So it deals with the cold formed steel standard cross-sectional shapes. Moving on to structural steel, we have, by the way, the main component of steel is the iron. Okay. So it was utilized as early as approximately 4000 BC. Of course, the mineral was scalded and then being heated in the charcoal and was formed as a tool like knives, swords, shields. So most of them are used as utensils, as a weapon in warfare, of course, and as a transportation parts. Okay. So cast iron and wrought iron, these are materials with a lot of impurities in it. So, but it was used in various types of bridges in the late 18th century and early 19th century. In fact, the Eads Bridge was first constructed in 1874 in St. Louis, Missouri. Okay, this is the first structural steel railroad bridge. We also have the steel framed building in Chicago, first building with steel frame in 1884. And then structural steel has already evolved into steel. This is an alloy of iron and carbon. So the carbon component actually tends to increase the strength of the primary material or component of the steel. It was first used in heavy construction in the 19th century up to the present. So of course, I think you are also familiar with the stress and strain diagram, because we need to recall and understand the concept of the behavior of your material, especially steel material that behaves as plastic or ductile in nature. So this is the strain diagram. Denotes the graph for the relationship between the unit load, or that is expressed in sigma, or the force all over the area. Okay, so this is the applied force. And we also have the unit deformation acting on the abscissa, and that is expressed into deformation all over the length. So in short, it is the relationship of the loading and the elongation and deformation of your material. So by the way, this is a pull test of a material, especially steel, that is gripped on both ends. Okay, and then the force is equally distributed. Finally, the deformation is observed. Okay, so to summarize that concept, in here, the relationship will come into 4 stages. First, we have the elastic, the plastic, and the strain hardening, and finally the necking and the failure. So the first stage is the elastic limit. So within this elastic limit, Hooke's law applies. So of course, the Hooke's law is the ratio of the stress to the strain. So it is represented by the Young's modulus of elasticity. So within this limit, as you can see, as we increase your load, okay, there is also an increase in your elongation or deformation or the strain. In short, they are directly proportional. Hence, Hooke's law can be applied. So next to it is the elastic limit. So in the elastic limit, we have the upper yield, okay, upper yield point as well as the lower yield point. So in this case, we can now count or measure certain permanent set or permanent deformation on the material. Meaning, if we unload the material, the deformation will not be restored back into its original position. Unlike on the proportional limit, if the load is removed from the material, the elongation will be restored. Okay? Will be restored. So permanent deformation would be observed here. Okay, starting at the upper yield point, the stress is no longer directly proportional to the strain. So the next stage will be from the upper yield point to the lower yield point. So at this stage, plastic zone is also called as the yield zone, where the material behaves like plastic. So meaning, a certain slight increase, slight lang in the loading would cause very much or appreciable elongation. So this is the plastic behavior of your steel. So that is good indication of the strength of the steel, the ductile behavior. So the importance of the ductile behavior is that at the time of failure, you will have a caution. It will provide a caution for the designer. And then here, within the yield, upper yield point, it is denoted by Fy, or Fy is actually the yield stress or the yield strength of your material. That is Fy. So of course, an additional loading, a slight increase in the loading, of course, you can see a slight increase in the loading will cause an appreciable deformation on that strain hardening stage. And by the principle of Poisson's ratio, the yielding shall be associated with the reduced cross-section on the material. So ninipis yung material because of that. Until it will reach the ultimate strength denoted by Fu. Until its rupture. So this is true actually to material with ductile behavior, especially on steel section. So as you can see on the section here, there will be a necking, an observed necking in the failure. That is a good indication of the ductile behavior of that material, which is advantageous in structure. Okay. There are notes here. Note that Fy is still associated with the proportional limit governed by the Hooke's law. Okay. So, yung yield point, i-apply pa rin natin yung Hooke's law because on the upper yield point, there is no permanent set yet, and that will be our threshold for the strength. And we also have here 0.002 or 0.2% strain is usually selected for steel, or this is what we call 0.2% offset method. And we note that whatever the shape of your steel, as long as it is made up of steel, the modulus of elasticity for steel is equal to 29,000 ksi, or kibs per square inches, or that is equivalent to approximately 200,000 megapascals. So notes on steel composition. As mentioned earlier, steel primary component is iron. So it has small amounts of carbon that adds to the strength but reduces ductility. So other components are copper, manganese, nickel, chromium, molybdenum, and silicon. So your ASTM provides, or the American Society for Testing and Materials provides, various properties of various grades of structural steel. This will be the grouping. We have the yield point, the tensile strength. By the way, A36 or ASTM 36 is the most commonly used, okay, with the following properties. Your yield stress is 36,000 psi. The tensile strength, or the ultimate strength, will be equal to 58 to 80,000 psi. A36 steel is classified as plain carbon steel. Okay, plain lang siya. So with the minimal amounts of carbon, phosphorus, and sulfur. So the structural steel sections comes with the hot rolled sections. Okay, it could be IH, tapered, flanges, parallel flange, equal angle, and equal angle. The structural T, the flat or square round, or the bars, what we call. So these are steel sections to choose from. So it could be also in the cold form sections. Steel sections to choose from. We have those shapes: equal angle, unequal angle, the lipped angle channel, the lip channel, and then the lip Z. Okay, so we have the common shapes of the steel sections. Actually, this has been made to be a standard for us to choose from. So these standards will be dependent on our selection. Okay, your design will be dependent on the selection of these standard structural steel sections. The important thing here is that we are familiarized with those sections and the dimensions, as well as the properties as a part of our design parameter. So actually, this is the W shape. So it is not a literal W shape, okay? So it has a web and a flange. By the way, the web is the stem inside the shape, wherein the outer stem are the flanges, okay? And in here, W18, or the 18 number, denotes the overall depth of the cross section, or the wide flange, while the 50 here denotes actually the weight in pounds per foot. So meaning W18 has a depth of more or less 18 inches, and it has a weight that is 50 pounds per foot of length. So that is the indication of the abbreviation as well as the code of your shape. Next here is we have the American Standard or S shape. So again, it is not literally S shape. So like the flange, it has a web and flange, okay, web and flange, but the S shape has sloping inside face as observed here, and a shorter flange thickness or outer stem thickness. So S18 here similarly denotes your overall depth of the section. So S18 has an overall depth of 18 inches, while the 70 here is also its weight in pounds per feet. So the dimensions, more details on the dimensions can be found in the Structural Steel Handbook provided by ASTM. So by the way, S-shape is also known as I-beam, or it is previously called as I-beam because of the shape. Of course, ito hindi mawawala to. The angle shapes. So these are commonly used locally. Okay, so the angle shapes could be equal leg angle or an equal leg angle. So this time we have the codes. The first number here, L6. L is the angle, then 6 denotes the depth of your angle, and the width is the second number here, okay, 6 and 4. However, the code does not denote the unit weight of your material. Anyway, you can just compute that right away by the density of the steel, which is 7,859.5 kilogram per cubic meter. So angle shapes has various thickness as well. Okay. We also have the standard or the American Standard channel, or what we call C-shape. So literally it is really C-shape. Okay. So the number here, C9, refers to the depth also. And then this refers to the weight, just the other sections. Okay. And like your S-shape, it has a sloping face inside the face. So thus increasing the moment of inertia. So subgroup is termed as miscellaneous channels. So may mga subgroup yan, wherein the miscellaneous channels are actually similar in cross section, but somehow it is not the same. Similar but not the same with those of the standard. Okay. Next, we have the structural T. So structural T is a split T. Actually, structural T manggagaling yan sa mga cut sections of the mentioned steel sections. Parang in-split nila yung ibang section, like the flange section, the standard S, or your I-beam or the channel will be split split, okay? May slice yon at magiging structural T. Kaya nga yung structural T can be WT or the parent section of WT is the flange or the W sections. While ST parang hinati yung American S shape. Therefore, the parent of ST or the parent structural T is the American S. Likewise for the miscellaneous. Okay? So, ganun din. 105 here refers to your weight in pounds per feet. Okay. So, WT as mentioned, flange section as parent section, ST, S section as parent section, MT, miscellaneous section as the parent section. Okay, aside from those structural steel sections to commonly use, we have also the bars and hollow structural sections. So, ito yung tinatawag na HSS. So, it could be round in the form or a square or rectangular pipe. Okay, of course, this was formed through bending of a plate. So, ibibend mo yung plate, magiging steel pipe or hollow structural sections. So, when that is done, it will be connected by a seamless welding para ma-connect yung ends ng bended plate to form a tube or pipe. So again, this is termed as steel pipe or the hollow structural sections, HSS. Just like the different shapes, may code din yan and different sizes as well as the thickness. Okay, so in here we have the build-up shapes. Build-up shapes are normally the combination of the existing shapes wherein we need to build them up for a larger inertia requirement, because on larger structures the mentioned single sections are no longer sufficient enough to resist. They need to be combined on the other shapes, okay, to increase their strength, of course, to increase also the moment of inertia that is essential in the design. Remember that the inertia is always present in your design formula, like the bending stress, that is MC all over I. Okay, so I think that ends our session for today. So thank you for listening and have a good day.